So hi everyone, I'm Adda Athanasopoulos-Zekkos. I'm a faculty member here at UC Berkeley in the Geosystems group, and similar to what Jason mentioned at the beginning of his presentation, this is also another one of those projects where certain elements of it were ongoing, and then the peer funding was really instrumental in allowing us to explore some other aspects. And so, of course, a lot of thanks go to Dr. Jong-sun Kim, who was a postdoc here for a couple of years and has now actually transitioned to an assistant professor position, Bo-Fei Zhu, who's the PhD student on the project, and of course, Misko Kupinovsky from New Zealand and Nate Wagner from Slate for their contributions. So first of all, we've been talking about gravels from the previous presentation, which is great because it has created a really nice baseline for me to start talking about, the topic. But it's sometimes we have to even describe why it's important to characterize these materials better than we do, and whether we actually find them. Sorry about that. Seems to be an incompatibility. But where do we actually find them, and why do they matter? Why are they important? Thankfully, by now, we no longer have to say why they're liquefiable. I think we can all agree that they can and will liquefy given the appropriate circumstances. But these materials can come in many different shapes and forms, meaning that they can be man-made fills, where we are more in control of their properties, the gradation, particle size, and whatnot, whether they contain fines or other types of grain sizes. But they can also be natural deposits. And actually something that we've been kind of exploring more as a follow-up to this project is that when they are actually naturally deposits, there's a lot of differences in the fabric, how they're depositioned, and so that actually we're seeing affects the response quite a lot. And so these materials can actually be quite critical on how they control the behavior of infrastructure. And we have seen that in a couple of fairly recent events at this point, 2014 earthquake in Kefalonia, Greece, and then the 2016 Kaikoura earthquake in New Zealand. Both cases we had poor performance in port facilities, critical port facilities, in part due to the liquefaction of these gravelly materials. In both cases, these materials were part of fill that was laid as part of reclaiming the land to develop the port, and we see that actually quite often in these locations. There is actually a wide range of other events. Some are better documented than others. This unfortunately comes with age, and so more recent events are much better documented thanks to efforts like GEAR and STEER and other type funded activities. And the reason why, I put a plug on for that is because we can actually learn so much from these case studies if we can analyze them, help us better understand what happens, given that in many cases, these types of events are nature's full-scale experiments for us, and so we try to make the most of them. And so we've been actually exploring the world, not just me, of course, but the others in our research group, and Kyle Rollins has been leading this effort, but basically trying to find these materials in different places so that we can also account for these types of variabilities that come with different geologic setting, depositional environment, different types of seismic zones and whatnot. And of course, again, kind of final piece on the motivation is that these materials can be very, very critical, especially here in California. There's a lot of dams that are being reevaluated or will be reevaluated. And we see these materials actually in both sides of the equation, meaning that they can be part of the dam materials. There you hope that there are some descriptions in the designs in terms of how they have been placed, even though that's not always the case. But these materials can also be part of the foundation zones. And so upon reevaluating these dams, you realize that there was a little bit of guesswork that was done, back in the day in terms of how they behave. And like Jason, I think, very nicely said, there's been a lot of extrapolation when it comes to these materials from things that we know from SAMs. And I will definitely second, that we need to be very, very careful and revisit a lot of those. And this is in part what we've been trying to do with our work. So our work, of course, I won't be able to touch on it, but as I said, includes many different elements to it. We are big believers in an integrated approach, and so we've been doing a lot of field testing, laboratory testing, analyzing case histories, some DEM analysis. I will only show certain aspects of the work here. I'll quickly start with the laboratory testing that we've been doing using our large-scale cyclic simple shear device that we have now here at Berkeley. This is a prototype device that was developed by us in collaboration with Geocomp back when I was still a faculty member at the University of Michigan. It can accommodate a 12-inch diameter specimen, and it uses the stacked rings approach for the application of the simple shear. This is what a specimen may look like, and a particularly nice feature of the device that we have included is the availability of either bender elements or accelerometers that will allow you to characterize the shear velocities of every specimen that we test. And you can do that at the beginning, at the end, sometimes during certain aspects of the testing. And it's really important because the shear velocity is a really good parameter to know, because it can basically give you information about the stiffness of the material. And also something that I particularly like is that it may be the connecting link between lab behavior and field behavior for these materials. We need to remember that with these materials, you cannot really have high quality, undisturbed samples. So what we test in the lab is reconstituted. And so trying to kind of link the lab and the field behavior tends to be rather tricky at times. And the shear velocity could, be a way for us to get there. We've been testing a variety of gravel types and gravel mixtures with sands, because we have also been targeting a wide range of gradation. Of course, you start simple, which is where the whole thing started with uniform gravels, which was eye-opening on its own. But then once you start mixing in other grain sizes, it really becomes very, very interesting. Just to kind of follow up on Scott's question, and on Jason's answer before, I'm definitely in agreement with using more of the void ratio, not the relative density. And even with the void ratio, when you have mixtures, and you have specific sizes that contribute, it's also a question of, well, which void ratio, right? Is it the overall, the global void ratio, as it's called? When you have the sand-gravel mixture, is it the void ratio of the gravel skeleton, of the sand skeleton? When is one controlling, when is the other one, right? And looking at the various percentages. So definitely the way to go, but more to explore in determining these types of thresholds. So in the lab, we've been developing, and at this point we have quite a large database of results for a wide range of these types of materials. Obviously repeating tests on sands that we have from conventional size devices, just for comparison. The mixtures, the plain gravels, we've been changing around the particle shapes, making them more angular, more rounded, bigger, smaller. This is really the big advantage that the laboratory offers you. You're in control, at least of those parameters. You can change them and really understand how they come into play. I think a big thing to note here, which is the reason why I keep showing this slide, even though it's one of our first slides and was on the peat gravel, which is a uniform rounded gravel, is that was really, I think, the first time that really hit us, how easy it would be for a gravel to liquefy even at an 87% relative density. And I've had to have, over the years, a lot of discussions with a lot of people who would come up and ask me and say, there's no way that's happening, it's not possible. But it is, right? And with these types of uniform materials, we now know that it happens. Why? Because again, of this problem with the relative density, that 87% and that 47% is not really giving me the information that's important, which is what void ratios do these conditions represent. And so when you're looking at a uniform material, these relative densities are actually void ratios that are much closer together. But when you're looking at a well-graded material, these void ratios are now much further apart, and there's a bigger difference in behavior. So there's more to unpack, right, in these results, and really to get down to the behavior of the materials. And of course, you see that once the gradation becomes better, and this is not even a very well-graded material, this is a gap-graded material, sand and gravel, but 40% of sand, all it takes to go from liquefying at 8 cycles to now liquefying at 19. Which is a pretty significant difference, right? And so it's really important to understand, how that comes to play. and how it ties to the type of gravel we're talking about, right, and the gradation of all the other materials. Now, what have we used our database? Well, we've used it to really develop these types of curves, the CSR versus number of cycles liquefaction curves, for a variety of densities and a variety of combination of materials. And the PIR project specifically allowed us to focus on gravels that were shipped to us from New Zealand, the Port of Wellington, so that we could develop these, and these are the ones that you see on your screen actually, so that we could develop these specifically before doing our numerical modeling so that we can use those for calibrating the various models. So the reason why these curves, are important is because they become essentially direct input when you're using models that will show you how your excess pore pressures are generated during the liquefaction phenomenon. So it's important that these are representative of the material you're trying to model. And this is really where the second part of the project came in with the numerical modeling. Just a final slide on the laboratory testing. Of course, it's really important to understand how initial stress affects these materials. I think this is another area where there has been a lot of extrapolation from what we know from sands. And this is an area where we said, okay, let's kind of revisit that and you know, try and fix that or make it a little bit better for gravels, before realizing that there was a little bit of fixing that was needed for sands as well, because a lot of the curves we've been using are actually based on rather limited amount of testing, typically of these uniform sands, which are more readily available in all our labs, right? And so I think, you know, we're all guilty of doing that at some point or another, but it's important, you know, when you're using curves, to really understand exactly what they're based on. And so these are the results for applying initial stress, shear stress conditions for gravels. This is one specific combination of the New Zealand gravels, well-graded gravel, and you see from the black line, which is kind of like that symmetrical back and forth, no initial shear stress, and then you start increasing from red to orange to green, and you get that bias, because at that point now you have your initial shear stress, and then once you start applying, it kind of moves you in a preferential direction. And then we can see how it will affect the number of cycles of liquefaction or the strain, right? So the behavior can be different because now you're a little bit closer to that envelope, but it may also just mean that, you know, you kind of stop at one place and you're just accumulating strain, but you're not collapsing. So we've seen a variety of responses, and I think very, very interesting results that we're actually in the process of publishing now. And so what that gets you is basically these new curves now, where you also apply the effect of the initial shear stress, and perhaps more important, because this is what we're more used to seeing, is what does that mean for this K alpha factor, which is the factor that I use to correct for the presence of initial stress. And so what we're seeing now with gravels is that the K alpha values are overall lower than the ones that we would expect if we were to just use the sand-generated K alpha curves. And that's important to note, because if you're lower, that means that you're pushed closer to 1 and perhaps below 1, and so the presence of initial shear stress is actually becoming detrimental. And so it's important, if that, you know, is present, to include that in your analysis. And then finally, the laboratory testing can also shed light into those post-cyclic volumetric strains. The good news here is that, at least with the caveat for the materials that we've tested up to now, is that overall the volumetric strain potential seems to be lower than that of sands across the board for the gravelly materials. So now, very, very quickly, just to give an update on the numerical modeling, and I wanted to primarily kind of highlight again, you know, why this is important to combine the two, because what we've been trying to do is use these case studies the way they have been traditionally used for sands to back analyze and learn all sorts of things, like lateral spread models that have been developed based on case histories, residual strength models that have been based on case histories. And so in trying to do the same thing for gravels, you realize that what you need to be careful with is, in order to use those numerical models, you need to use models like the one developed by Katerina and others that will model the generation of pore pressures. But these have primarily been based on calibrations with testing from sand materials when it comes to the cohesion of materials. So something that we've been trying to do through this project, and we hope to be able to establish by the end of it, is basically answer the question, are these models appropriate? Because I can still use them with some small modifications, let's say just a slight recalibration, or is there something overall a little bit more fundamental that has to be changed and perhaps warrants the development of a new model, right? And so we need to kind of establish that. And so I'm not going to go over in detail, but we've been doing that for New Zealand, the Port of Wellington, because as I said, it's a very well-documented case study, and we had NISCO send us the materials from there, so we have laboratory-developed curves for that. And we've used, these are just the input ground motion process that we used. Again, part of the fact that we have so much data is that you can have a really nice input ground motion. And then these are the profiles. And we've used basically 3 different pore pressure generation models: the PM4 sand, we have used the UBC sand, and then we've used the URS Roth model as it's known. And this is for the gravel reclamation fill, and then the other materials were modeled according to the parameters that we had from all the other testing. The testing for the site, by the way, includes shear wave velocities, CPTs, DPTs, you name it. It's a very, very well characterized site, which I think makes for a really great case study. And so these are just some details from the mesh. We decided, because there was actually liquefiable material that spanned the entire section of the port, to model the entire thing, which makes for very, very long runs, but allows us to see what's happening on both sides, because there were lateral spreads that were documented on either side. And so we used our laboratory developed curves. We used some existing CSR calculation procedures. We can calculate the excess pore pressures. You can see kind of like the light blue at the top in the edges where it's the liquefaction of the gravel. And then really, these are just details of the various models where we calibrate, but I do want to kind of quickly show this as the last slide here, where we see basically the comparison with real measurements for these displacements. So the dots are real displacements measured on site, and then the continuous lines are results from the numerical models. And we're trying to see exactly which aspects we need to modify or play with for the various models to get a better fit, so that we can hopefully answer this question that I posed earlier. You know, is it enough? Can I just kind of turn a few knobs here and there and make the model, do what actually happened, capture the overall behavior, or do I need to do something a little bit more than that? The bottom figure, that's not a very good match, because that's vertical movement that has to do with volumetric settlements, cracking, and other things that the numerical model is actually not built to capture, so we don't really expect an agreement there. And so, lastly, we also want to look at the K sigma and the K alpha effect, because some of these models will use K sigma or K alpha curves as a direct input, but other models don't, and they will calculate it as a result of the run itself. And so you want to see again how that works for these materials, now that you've seen in the lab that sometimes these materials don't follow the trends that we think have been established for the sandy materials. And so for our next steps, we want to continue looking into the differences in the runs for the 3 constitutive models that we've been using. We also want to study the effects of the sublayering, because there are some sections where there's some thinner layers that are in between the reclamation fill, and we want to see that effect. And then finally, better understand and quantify the soil structure interaction effects from the presence of the wharfs that are there. So with that, I'm just going to thank our sponsors and my collaborators, and again, feel free to email me with any questions you may have.